Beams provide a good introduction to the general stiffness method applicable to frames, because in a beam, the local coordinate system and the global coordinate system are identical. So in this problem, we will use the stiffness method to find reactions for a beam. The key concepts we will use are compiling the structure stiffness matrix for a beam, calculating fixed end forces for a beam, and calculating reactions given deformations. And here's our beam. It's continuous from node 1 through node 3, fixed supports at node 1 and 3, and a roller support at node 2. E and I are constant for the entire beam. And here's our approach. We'll begin by approximating the answer. That way, when we're complete with our stiffness analysis, we'll have something to compare against to evaluate whether we have reasonable results. Then we'll compile the structure stiffness matrix. As the first part of our stiffness method approach. We'll calculate the fixed end forces. And we'll use that information to find deformations. In this case, the deformations are rotations or slopes. And we'll find reactions, specifically the moment reactions, and we'll finish by comparing with our approximation. Now step 1. Approximate the answer. If we take a look first at member 1, it sort of resembles this situation. In this situation, we can find the moment reaction at the end, M2, from a formula inside the back cover of our text. And it's given by PL over 8. And we need to pay attention to our directions. On the left end, it is counterclockwise, and in the stiffness method, we draw a positive moment as counterclockwise. So our approximation for the moment at degree of freedom 2, that's degree of freedom 2, not node 2, PL over 8, and that's positive in the direction drawn. So we have 25 kilonewtons times the 6 meters divided by 8, and that equals a positive 18.75 kilonewton meters in the direction drawn. Well, member 2 sort of resembles a fixed beam under this situation. So the moment reaction at node 3 is degree of freedom 3, so we'll call it M3. And from the inside back cover of our text, we see the moment is omega L squared over 12, and this one is clockwise, so we will have a negative omega L squared over 12, which is a minus 15 kilonewtons per meter. The length is 4 meters. We'll square that over 12, and altogether that gives a minus 20 kilonewton meters, where positive is counterclockwise. And now step 2. We'll begin the stiffness method process by assembling the structure stiffness matrix. But to do that, we have to first develop the element stiffness matrices. We'll start with element 1. Equation 15-1 provides a relationship between deformations in local coordinates and forces in local coordinates. But for a beam, the local coordinate system and the global coordinate system are the same. So this is the element stiffness matrix, little k. And we have near node y prime direction, which would be shears, near node z prime, which would be moments for forces. In terms of displacements, they are, or deformations, this is vertical displacement, and this is rotation. Now if we look at our elements, both 1 and 2, we're not concerned with calculating the vertical reactions, so we don't need the rows associated with the y prime forces. So we don't need these or these coefficients. And if we look at this particular structure, the vertical deflections are all going to be 0. So this and this will be 0, which means regardless of what the coefficients are here and here, their contributions will be 0. So that means I only need these coefficients for my element stiffness. Well, common to each of those is L. So for element 1, L equals the 3 plus 3, 6 meters. So we have some coefficients will be 4 EI over L. If we pull EI out, we'll need 4 over L. 4 divided by 6 meters gives us 0.667 per meter. Some of the coefficients are 2 EI over L. If we pull the EI out, 2 over L, the 2 over 6 meters will give us 0.333 per meter. And so the stiffness matrix for element 1, EI is common to all of the terms. We have 4 EI over L, which is 0.667 over meter times the EI, 2 EI over L, 0.333 EI per meter, the 2 EI over L, and 4 EI over L. Now this refers to the near node rotation, And so that's degree of freedom 2, the way we have it labeled for this beam. This is the far node, and since this is near node and far node for element 1, this is degree of freedom 1. Now element 2. Its length is 4 meters. And so if we factor out the EI, 4 over L will give us a 1.0 per meter. 2 over L will give us a 0.5 per meter. And so the element stiffness for element 2, EI is common to all of the coefficients. 4 EI over L for this member, then 2 EI over L, 2 EI over L, and 4 EI over L. Our near node for member 2 is node 2, so that's degree of freedom 1, and at the other end, degree of freedom 3. And now to assemble those element stiffnesses to make the structure stiffness matrix. And we'll denote that one by capital K. So it's the element stiffness from element 1 plus the element stiffness from element 2. And this addition is by degree of freedom number. So for example, entry 1, 1, that is the force generated at degree of freedom 1 due to deformation at degree of freedom 1, is given by the component from element 1, or coefficient from element 1, plus that same designated coefficient, degree of freedom 1 and 1, from the second element. And in this case, degree of freedom 1, 1 is 0.667 per meter from element 1. From element 2, degree of freedom 1, 1 is 1.0 per meter. Both of those multiplied by EI. And together, the coefficient K11 is 1.667 EI per meter. Now, degree of freedom 1 is the only degree of freedom common to both members. So all of our other coefficients, 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2, we can obtain from one element. There won't need to be any addition. So our element stiffness equals EI, which is common to all terms in the structure stiffness matrix for this case. We have degrees of freedom 1, 2, and 3. 1, 2, 3. So we said that the force generated at degree of freedom 1 due to deformation at degree of freedom 1 is this quantity. And we pulled the EI back out front. Then for coefficient 1, 2, we pull it from this matrix, row 1, column 2, 0.333. This entry, row 1, column 3, comes from element 2. Then row 2, column 1, comes from element 1. Row 2, column 2 also comes from element 1. Row 2, column 3 cannot be found for this structure because degrees of freedom 2 and 3 are not connected by a single element. Row 3, column 1, we find from element 2. Row 3, column 2 will also be 0, again for the reason that degree of freedom 2 and 3 are not connected by any element. Then 3, 3 comes from element 2. Now we'll use parts of this matrix in this equation in order to find the unknown displacements at the unconstrained degrees of freedom. And we use this chunk of the stiffness matrix if, let's make that a K, if there are known displacements, for example, support settlements or support rotations. In this case, we know that all of the supported degrees of freedom have 0 deformation, so we won't need this portion of the structure stiffness matrix. But we also add our known loads, or load degree of freedoms, the fixed end forces. Once we solve this equation for unknown displacements, and I want to point out the subscript 1,1 is different than this subscript. This referred to a single entry, the force at degree of freedom 1 due to deformation at degree of freedom 1. This refers to forces at unconstrained degrees of freedom due to deformations at unconstrained degrees of freedom. Once we have those deformations, we can find our unknown forces, which are the reactions, using other portions of the matrix. Again, in the case of this problem, that is 0, and our fixed end forces at degrees of freedom that are constrained. That is, supported degrees of freedom. These are the fixed end forces at the unconstrained degrees of freedom. So we will need these two chunks from the overall structure stiffness matrix, our unsupported, our unconstrained or free degrees of freedom are just degree of freedom 1. So I'll divide between columns 1 and 2 and between rows 1 and 2 this part, which turns out to be just one coefficient, is the structure stiffness matrix, forces at unconstrained degrees of freedom due to deformations at unconstrained degrees of freedom. And this chunk down below the dotted line are forces at constrained degrees of freedom due to deformations at unconstrained degrees of freedom, and it has 2 entries. Now step 3. We need to find the fixed end forces. And let's start with member 1. We have fixed end force at the near end in the z direction and the far end at the z direction, meaning moment. And if we go to the inside back cover of our text, for fixed, point load in the middle, we have PL over 8 is the fixed end moment at each end. At the left end it is counterclockwise, at the right end it is clockwise. And since we consider counterclockwise positive for the stiffness method, we have a positive PL over 8 at the near node and a negative PL over 8 at the far node for member 1. And so for member 1 we have 25 kilonewtons times the length 6 meters divided by 8, and we have a negative 25 kilonewtons times 6 meters divided by 8. And so for member 1, our fixed end forces are a positive 18.75 kilonewton meters and a negative 18.75 kilonewton meters. And this is degree of freedom 2 at the near node and 1 at the far node. Member 2. Again, we have only 2 fixed end forces because we're not considering the vertical displacements or the vertical forces. If we look inside the back cover of our text, fixed, uniform distributed load creates moments of omega L squared over 12 on each end, counterclockwise on the left, clockwise on the right. So we have omega L squared over 12 and minus omega L squared over 12. And for member 2, where this is our near node and this is our far node, we have the 15 kilonewtons per meter times the 4 meter length squared divided by 12 and minus the 15 kilonewton per meter 4 meters squared divided by 12. And for this member then we have fixed end forces of a positive 20 kilonewton meters and a negative 20 kilonewton meters. Degree of freedom at the near node is 1 and at the far node is 3. So for the entire structure, the fixed end force for degree of freedom 1, 2, and 3 is given by the summation of the fixed end forces from each of the members. So for degree of freedom 1, we have the negative 18.75 kilonewton meters, and we add the 20 kilonewton meters. For degree of freedom 2, we have only the positive 18.75 from member 1, and for degree of freedom 3, we have only the minus 20 kilonewton meters from member 2. When we add these, we get a positive 1.25 kilonewton meters, 18.75 kilonewton meters, and a minus 20.0 kilonewton meters. Those are the fixed end forces for the entire structure. We now have all the information we need to apply the stiffness method to find the deformations. And the equation we use for that we saw previously. The forces at unconstrained degrees of freedom are known. They're the applied forces directly to the degrees of freedom, equals the portion of the structure stiffness matrix that is the forces at unconstrained degrees of freedom due to deformations at unconstrained degrees of freedom, and those deformations are given by capital D sub U, and to which we add the fixed end forces at the unconstrained degrees of freedom. Well, there's only one unconstrained degree of freedom for this structure, and that's degree of freedom 1. The applied couple moment at degree of freedom 1 is 0. The coefficient is 1.667 EI over meters, times the deformation at degree of freedom 1, which will be the slope or rotation at degree of freedom 1, and the fixed end force at degree of freedom 1, which we found to be 1.25 kilonewton meters. Well, if we solve this equation for the deformation at degree of freedom 1, we get a minus 0.750 kilonewton meters squared divided by EI. And we can use that information, that deformation, to find the reactions. And to do that, we use the equation where the unknown forces at constrained degrees of freedom or supported degrees of freedom equals K21, which are all of the coefficients from the structure stiffness matrix that are associated with forces at supported or constrained degrees of freedom due to deformations at unconstrained degrees of freedom. And we add in our fixed end forces at the constrained degrees of freedom, that is, the supported degrees of freedom. we have two supported degrees of freedom. Degrees of freedom 2 and 3. And to find those, we'll use the portion of the structure stiffness matrix, which we identified as this chunk, and 0.5 EI per meter times the deformation. There's only one deformation in this case, minus 0.75 kilonewton meter squared over EI, and to which we add the fixed end forces at the supported degrees of freedom or constrained degrees of freedom, which are these. And minus 20 kilonewton meters. So if we multiply this vector by this constant, I get a negative 0.25 kilonewton meter. The EI's cancel and one of the meters cancels, and to which we'll add the fixed end force 18.75 kilonewton meters. Multiply these two, I get a negative 0.375 kilonewton meter, to which I add this fixed end force, the negative 20 kilonewton meter. We put those two together, or we put each of these pairs of terms together. The resulting reaction at degree of freedom 2 is 18.5 kilonewton meters, and at degree of freedom 3, 20.38 kilonewton meters. At degree of freedom 2, degree of freedom 3. Now step 6. Let's compare results. And we'll do that so that we can evaluate the reasonableness of our stiffness method results. From our approximate analysis, we found the moment at degree of freedom 2 would be approximately 18.75 kilonewton meters, and that's positive, meaning counterclockwise. So we have a positive 18.75 kilonewton meters. Moment at degree of freedom 3, we approximated as a minus 20. And that's kilonewton meters. And again, our sign convention is counterclockwise is positive. From the stiffness method, we found the moment at degree of freedom 2 to be 18.5 kilonewton meters, and at degree of freedom 3, minus 20, we'll round it off at 0.4 kilonewton meters. When we compare the results, they're actually very similar, so we conclude that our stiffness method results are reasonable. Now I will point out our approximate analysis results were basically our fixed end forces, and so what we observed is that the continuity of the problem doesn't change the moments at the ends significantly compared to the fixed end forces if everything was fixed supported at the ends. So now let's go back and review the process we followed to get here. We started by approximating the answer and looking at this continuous beam with fixed supports on each end and saying that each beam segment, each beam member, is kind of like a fixed beam. And so we used information inside the back cover of our text to approximate the moment reactions. We then began the stiffness analysis method by constructing the structure stiffness matrix, and to do that we began by assembling the element stiffness matrices K1 and K2, and we did so only for the rotational degrees of freedom, because in this problem we're only concerned with moment reactions, and the only unconstrained degrees of freedom are rotations. We then assembled that structure stiffness matrix and partitioned it so that we knew which chunks to pull out to find displacements and to find reactions. We then calculated the fixed end forces for each of the two members and then assembled those into fixed end forces for the entire structure. We used that information to find the deformations. In this case, there's only one unsupported degree of freedom that's a rotation, and that's degree of freedom 1. And then we found the two reactions given that deformation. We then compared our approximate analysis results to our stiffness method results, found that they were in fairly close agreement, and concluded that we have reasonable prediction of the moment reactions for this continuous indeterminate beam by using the stiffness method. Well done.